Hi everyone, today I will share with you a one-click RNA-seq pipeline using Snakemake. With one click you will go from FASTQ files to a table of differentially expressed genes. This is the code that will launch the pipeline, and as you can see it's less than 50 lines long. In this video we are not going into the details of how to run each command in the RNA-seq pipeline. That we cover in another video. This video is about how to level up your bioinformatics skills by automating your RNA-seq pipeline. We are going to be using the workflow manager Snakemake to create the pipeline. If you are unfamiliar with Snakemake, do not worry. I will give you a sense of what the different snippets of code do, and you will notice that the language used is very intuitive. So let me walk you through what the pipeline will be doing. Snakemake can provide us with a picture of the workflow, and for that we need to run the following command. Once we do that, we get this diagram. The first thing that the pipeline does is to map the FASTQ file to the reference transcriptome. This is done for every RNA-seq library, and we have 6 libraries, so we have 6 branches here. For each library, we need to do a sum to bank conversion and the quantifications. These are these steps over here. Once we have all the quantification files for all the libraries, we run this seq to generate the final table with differentially expressed genes. So if you want to run this pipeline without the workflow manager, you will need to type these 19 commands manually, which is error prone. And also you need to wait for each command to finish to launch the following command, which makes running the pipeline more time consuming. Before we launch the pipeline, we will do a dry run that will help us understand the script. I have previously run the pipeline, so I have all the intermediate files that the pipeline will generate. For simplicity and to avoid running everything from scratch, I will remove all the intermediate files for only one of the libraries. In this way, the pipeline will have to run the steps just for a single RNA library. The diagram shows again all the rules, but those that already have the output files are marked with a dashed line. To request the dry run, we run the following command. So here we are shown what is going to happen. This information will help us understand the script that we are using. What we want from this pipeline is the final table with differentially expressed genes. This is what we specified in the rule all. To get the final table, we need to run the final table rule. The pipeline also tells us that some other rules need to be run to get the missing file from our list of input files. To generate the list of input files, we use the list with the RNA libraries IDs and this function to generate the input files that we need for this rule. Okay, let's slow down a little bit here because this is the key to Snakemake and workflow managers in general. I've been trying to figure this out on my own, and it was quite challenging to understand this concept of propagation of wildcards. So let me show you what this means in this example. In this case, we have this input for the final table, and it's this bunch of transcripts over here. So let's go ahead and copy this here. I will just comment them because it's not part of the code, it's more like a metadata that we have. So this will be, in this particular case, the input that we have. So we have all of these files, for example, shown of the first one. So what Snakemake will do is we'll try to see which of the rules match this format in their output, and then we'll run that rule. So here we have like 3 rules: the quantify, the convert, and the mapping. And it's in this rule quantify that can actually give us something with this format, because it has this view, the run, and ends in this quant SF. So the pipeline will do exactly that. So let's add this metadata, this output, and this will be matching actually what we have here. And this, what is in bracket, will be our wildcard. So what the pipeline will do will take this as a wildcard and then we'll generate this input. So you see here that we are going from the output to the input. So we are going from the back to the front of the pipeline. So here we have the input, and in this case the input will be this thing dot bam. So now the pipeline will do exactly that same reasoning. It will look for a rule that has this view.bam as an output. And here we have two rules left. Rule convert actually is producing as an output that .bam. So this is the rule that we would like to run. In this case, the input of the previous rule will be the output of this one. And then this rule will generate this input. And the pipeline will try now to find a rule that has this as an output, and there is only this rule remaining, so of course will be that one. Then this rule will need this FASTQ as an input. So in this case, the pipeline knows that this file already exists. It will not require any other rule to generate this, because this is a file that the pipeline can find in the computer. And this is when it comes to the end, and this therefore will be the first rule that will be run. Okay, with that in mind, that manual propagation that we've done, let's see how this is documented in the dry run. The file that we are missing is the one ending in 21, quant.sf. To get the quant.sf file, we need to run the rule quantify. And to run the rule quantify, we need the corresponding .bam file that we get with the rule convert. And so on and so forth until we reach the rule mapping that does not depend on any other rule, because the input is our FASTQ. When we launch the pipeline, actually all of these steps are run and we get our final file. Before we finish, let me clarify these Docker lines over here. To run the pipeline, I use Docker images, which are a type of virtual machine with programs needed pre-installed within them. This makes the pipeline easier to replicate and share. However, if you have all the programs already installed in your computer, you can simplify this line from this to. In the final command, we are not launching one-liner, but we are calling an R script. This is the script that runs the DEG and gets all the metadata. If we upload the file that the script just generated, we get this table with the differentially expressed genes that we were looking at. I will leave the link to the code and the metadata in the description for you to use. Well, that's it for today. If you like the content, please subscribe to the channel. This will make the content more accessible to other people like you, including yourself in the future. And now that you have your table of differentially expressed genes, do not forget to check this video on how to do gene ontology analysis with us, and I will see you there.